we have an extended version of WACCM called WACCM X, which goes up even higher to 500 to 700 kilometers. That's used for space physics. So I mentioned the stratosphere, and the stratosphere is defined by the ozone layer. Basically, the stratosphere is the region above the troposphere, where the troposphere is where, as you go up in altitude, the temperature is decreasing, and the stratosphere, as you go up, the temperature is increasing. And the reason is because we have an ozone layer that's absorbing a lot of energy from the ultraviolet rays of the sun and heating up, and that produces an increasing temperature, making the stratosphere much more stable because you have warm air over cold air, and you don't have the weather that we have in the troposphere at all. And then once you get above the ozone layer, the temperature starts decreasing again in the mesosphere. So in comparison to CAM, we have, as I mentioned, a higher top near 145, 150 kilometers. It's actually 5 times 10 to the -6 hectopascals. The standard version of WACCM has 70 vertical layers, WACCM 6, compared to 32 in CAM 6. And it also includes interactive chemistry in different chemistry packages. We have one that is the middle atmospheric chemistry, which you can use to study the chemistry of the ozone layer. And it includes heterogeneous chemistry on polar stratospheric clouds that cause the ozone hole to form every spring in Antarctica, as well as ozone loss in the Arctic. And we have heating due to chemical heating rates in the upper atmosphere. That's the basic middle atmosphere chemistry. And then there is what we call TSMLT, which has a lot more chemistry in it. This is for troposphere, stratosphere, mesosphere, and lower thermosphere. And that adds on to the middle atmosphere chemistry by putting a bunch of reactions and species that are important in the troposphere for air quality, for studying pollution and effects of that. So this is sort of combining what used to be done in CAM-Chem with WACCM. So we have a complete model that includes all the chemistry. And now we have prognostic stratospheric aerosols from sulfur emissions from various sources, some of which are volcanic eruptions that can put a lot of sulfur into the stratosphere. And we'll talk about the effects of those. It also includes ion chemistry in the mesosphere, lower thermosphere, and all the processes associated with that, as well as the aurora, precipitation of energetic particles from aurora in the polar regions, and solar proton events that can happen and affect the chemistry of the upper atmosphere. We have extreme ultraviolet light, which penetrates into the upper atmosphere, and we have non-local thermodynamic equilibrium, which is important once you get up into the mesosphere, because the radiation behaves differently up there than we assume in the lower atmosphere. We'll talk about the effects of gravity waves, which are vertically propagating waves in the atmosphere from air moving over mountains, over fronts, and over convection, and that affects the whole dynamics of the upper atmosphere. We have an interactive quasi-biennial oscillation in the tropical winds derived from wave forcing. We'll talk about that. And another thing that's important once you get up above 80 kilometers is molecular diffusion, which means unlike in the lower atmosphere where you assume everything is very well mixed, all the long-lived species have pretty much constant mixing ratios. Once you get up above 80 kilometers, the molecules start separating by molecular weight, the effects of gravity, because there's much less air density and much less mixing up there. And then we have the even higher top version of WACCM, WACCM-X, which is goes into basically the edge of space. So the motivation for WACCM is comes from this monograph from the year 2000, which talks about a desire to model coupling between atmospheric layers and to interact chemistry and dynamics, as some of these are listed here, and also to model climate variability and climate change, and the importance of changes in the composition of the atmosphere on not just the overall warming, but also the dynamical feedbacks and impacts on the ozone layer. And finally, WACCM is very useful in interpreting satellite observations, especially when you nudge it with specified dynamics, as we'll talk about. So this is these are the components of CESM2. We have land, ocean, sea ice, and land ice components. And then for the atmosphere, the default component is CAM, and you can also choose other components. Simone will talk about CAM next, but WACCM and WACCM-X are also alternative versions to the default version of CAM. They are versions of CAM. So this table lists the full details of WACCM and WACCM-X. I mentioned there's a specified dynamics nudged version of WACCM. We'll talk more about that, but that has an increased number of vertical layers because we want to use the same levels as the meteorological analyses that we're nudging to. WACCM-6 runs at 2 different horizontal resolutions, basically 1 degree approximately, or 2 degrees approximately, 1 by 1 or 2 by 2. Details are shown there. WACCM-X basically runs at 2 degrees. And the time step for WACCM-6 is the same as CAM, 30 minutes, but WACCM-X uses a 5-minute time step because of faster processes happening in the upper atmosphere. And then you can look at all the different details there comparing these models. So when we run WACCM, we have to choose configurations, and you can, as you probably learned, run the components as either free running or driven by observations or climatology for the ocean, land, and sea ice, and that all applies when you're running WACCM. Basically, we always run WACCM with an interactive land model, but you can choose data ocean or data sea ice or interactive ocean or interactive sea ice. And then for the chemistry, we can choose something called specified chemistry, which is even more simplified than the middle atmosphere chemistry, and it's closer to the chemistry that CAM uses. And that is used when we want to study the upper atmosphere dynamical processes and we're less concerned about chemistry. So we use prescribed ozone the way that CAM uses. And then we can run free running interactive chemistry, or we can nudge the dynamics with specified dynamics. And for each of those, we have to choose whether we're going to run a static case, like a constant pre-industrial or a constant year 2000 or year 2010 or something like that, or a transient. And when you're running specified dynamics, nudging it, you have to use the transient because of the dynamics are transient. So here is a discussion of specified dynamics. We are nudging the winds and temperatures to analyses from GEOS5 or MERA, and we can choose to nudge the nudging strength. Basically, we give a relaxation time, which can define something like nudging towards 1% per time step towards the analyses, which are basically a form of the observations of winds and temperatures, or we can make it stronger, something like 10% per time step. And then the chemistry and radiation interact on top of that. Talking about the gravity waves, we have three kinds of gravity waves. There's the orographic gravity waves, which is air moving over topography, mountains basically. We have air moving over fronts at mid-latitudes, which can affect the dynamics at mid and upper latitudes in the upper atmosphere. And we have air moving over convection over the tropics, which can affect the dynamics, because these waves, they move up in the atmosphere until they break and deposit energy up there, and that drives the whole circulation of the upper atmosphere. And sometimes we refer to the convective gravity waves as the Barris scheme, which is for Jaga Barris, which is the maiden name of Jaga Richter. So just so you know, there's another paper by Richter in 2010, which explains the details of this. And Jaga Richter's also worked a lot with Rolando Garcia on our interactive quasi-biennial oscillation in the tropical winds, which is a shift between eastward and westward winds about every 27 months there. And it's shown in the top in the observations. And in the middle, we have a higher resolution version of WACCM 6, which is 110 levels. I mentioned 70 levels and 88 levels. This is even higher. And that produces our best model version of the QBO, which you see here comparing very well to the observations. The default version of WACCM 70 layers does produce a QBO at 1 degrees, but it is not nearly as good as the 110 levels. The WACCM reproduces what's known as the water tape recorder, which is a phenomenon that's been observed of the seasonal oscillation in water in the tropics due to the temperature variation of the water in the stratosphere is controlled by the temperature of the tropical tropopause, and so water freezes out as it goes up into the stratosphere, and so you get this tape recorder effect if you look at it in altitude versus time of water oscillating due to that temperature effect. And we have a slight half part per million bias in the summer, but generally do a pretty good job. And WACCM is shown on the bottom 3 in different configurations: SD free running with AMIP, meaning with data, ocean, and sea ice, or a free running coupled with an interactive ocean and sea ice. And I mentioned the stratospheric aerosols, and some of those are affected by volcanic eruptions. So we have a database of volcanic eruptions from 1850 to 2016. Actually, now it extends further towards 2021 or 2022. And this is a visualization showing the energy and the amount of SO2 is the color of the different circles of these volcanic eruptions, and the latitude is on the vertical axis and time on the horizontal. So this big dark one in 1991 is Mount Pinatubo, and we have a lot of medium and small eruptions happening since the year 2005, which are also important. This is an animation showing these eruptions in WACCM. Here we have a couple in 2008 and 2009 in the Aleutian and Russian islands at high latitudes. And then in 2011, in this, we're going to see 3 different eruptions at 3 different latitudes happening, which put aerosol in the stratosphere. Here's one in 2014 in tropics, and we can see it's staying first in the tropics before spreading out to the southern hemisphere. And then this Calbuco eruption in 2015 in southern Chile led to what then became the record large ozone hole that year, which was recently exceeded because of another aerosol event of wildfires putting more aerosols from Australia. Okay, so we've done a lot of comparison of the stratospheric aerosol optical depth compared to observations, LiDAR observations at different latitudes. And so you can see here the effect of the eruptions in 1982 of El Chichon in Mexico, in 1991, Mount Pinatubo in the Philippines. And then more recently, since the year 2005, we have these small and moderate eruptions. And WACCM is shown in red and blue in different configurations. And then we see LiDAR in the other colors, black and green and yellow, and generally doing a pretty good job of comparing to the observations and the variation due to volcanic eruptions. We care about this because aerosols have an important effect on a number of important effects on radiation. Basically, they scatter sunlight back out into space, and so they can cool the surface. They also absorb the Earth's infrared radiation, and so they can heat the stratosphere when that happens. So here we're looking at the changes in the radiation compared to observations from the ERBS, Earth Radiation Budget Satellite, in black. And WACCM runs these are nudge specified dynamics runs. In red, we see WACCM with volcanoes. In blue, WACCM without volcanoes. And when we include the volcanoes, we do a really good job of matching the satellite observations there of reduced absorbed shortwave and outgoing long-wave radiation. We also reproduce very well the heating of the stratosphere by volcanic aerosols, and particularly you can see this this peak after 1991 and after 1982 of these El Chichon and Pinatubo eruptions. The aerosols are absorbing the infrared radiation and heating the stratosphere, and that's compared. WACCM in red and black shows radiosonde observations of those temperatures. This is the long-term global warming in coupled WACCM. We did 3 runs of this historical, and shown in red, yellow, and green, compared to the CESM ensemble in the blue shade, where we did many more ensemble members. And the observations are the black solid and black dashed lines. These are all normalized to, I think, the period 1920 to 1980. And we're reproducing the observed global warming with a lot of the cooling effects of these volcanic eruptions, which you can see on the top part, where we're looking at the stratospheric aerosol optical depth from volcanic eruptions in an inverse way to represent the cooling their effects. And the stratospheric aerosol also affects the polar stratospheric clouds, which are key to ozone loss in the Antarctic and also in the Arctic. And so here we're comparing to observations in black, and we have WACCM calculations of Antarctic on the left and Arctic in the right. In different configurations of WACCM, the free-running coupled ocean in blue, and green showing with a data ocean model. And finally, when we constrain WACCM with specified dynamics in the purple, we really reproduce well the interannual variation up and down of the ozone hole in the Antarctic, as well as the ozone loss in the Arctic. And this is just showing the 1 year, the year 2011, which was at the time a record large ozone hole. In WACCM shown on the top. This is after that Calbuco eruption in Chile, and the OMI observations on the bottom. And WACCM is really reproducing the total ozone globally very well, shown here. And that's only possible with having these interactive volcanic eruptions in there. All right, that's all the time I have. So here's contact information for me if you have further questions, and Simone. And I'm wondering why we have the same phone number, but look into that. All right, thank you.
So before we move to Simone, we do have time for like 1 or 2 questions if there are people have questions for Mike. And if you do, please come to the microphone just so you can, because we don't have a roaming microphone. So just come to the microphone here, please.
I had a question about how the volcanic eruptions are characterized in the WACCM model. So for ones before, like where we have remote sensing, how do we estimate the aerosol load and the magnitude and all that? Is that sort of like, and is there uncertainty surrounding with that, and how does that impact sort of the effects?
Yeah, so we basically derive the aerosol from emissions. So we have a database of volcanic eruptions and estimates from observations of how much sulfur they put in at what altitude. And there are uncertainties in both of those, particularly when you get before the satellite era, but also after the satellite era. And so those parameters can be adjusted to achieve some different results. Also, if you put in the same emissions in different ensemble members of a free running model, they're going to get blown to different parts by the winds to different parts of the globe. So in particular, something like a big eruption like Pinatubo in the tropics, sometimes some of it'll go more into the southern hemisphere and sometimes it'll stay more in the northern hemisphere. But the constraining that behavior based on observations is difficult as well, and particularly in the case of Mount Pinatubo, because there was another big eruption just exactly 2 months afterwards in the southern hemisphere. So we were uncertain about how much of the observations are from that eruption versus Pinatubo. But after we run WACCM interactively with these volcanoes, we use that to prescribe aerosols in CAM for those runs without interactive aerosols. And we believe that after comparing to observations, that is actually better than other databases where they try to prescribe stratospheric aerosols, such as was done for CMIP6.
Thank you.
Hi there, my name is Aaliyah. Great talk. I had a quick question about the WACCM suite. I'm interested in actually doing simulations with atmospheric hazes. Is that a suite that possibly is in the works or something that WACCM could be utilized for?
Atmospheric hazes?
Yes.
I don't know what that is. You mean on other planets, or?
It could be for exoplanets or it could be for early Earth templates.
Oh, I see. Yeah. So like organics.
Organic hazes, yes, hydrocarbon hazes.
Yeah, I mean, there are people who have adapted WACCM and CAM-CHEM for other planets. We don't necessarily have the capability to support that, but people at other universities and, for example, Brian Toon at the University of Colorado and his students have done a lot of modeling of planets, including the moon Titan of Saturn, which has those, I forget what you call them, those aerosols.
Yeah, hydrocarbon hazes.
Yeah, hydrocarbons, right.
Yeah, I was just curious, that's all.
It is, it would take a bit of work, but there's a community of people who've done some work on that you could get in contact with. You might try contacting Brian Toon at the University of Colorado if you're interested in that.
All right, thank you.
Mm-hmm.